All right, here we go. We're ready for in 6.1, we're ready for problem number 12. And here it is, and here's our job. So we want to find this random point D so that the coordinates of vector AC are the same as the coordinates of vector DB. So the first thing we'll do is find AC. So from A to C, from 1 to -1 is -2, backs up 2. And from -2 to -5 backs up 3. So we're coming from A to C, so 1 to -1, -2 to -5. Okay, so whatever's going on here, here's point D, don't know where it is, but point B is -3, 4. To get from here to here, this is how I'm moving. Vector AC and vector DB move the same way. So they both back up 2 and go down 3. So if I need to figure out where do I start so that if I back up 2, I'm going to end up at -3. Well, I think I'll start at -1. Does that make sense? That if I start at -1 and back up 2, I'll end at -3. Remember, B is my end point, my terminal point if we're using vector vocabulary. Okay, now where do I have to start? So that if I back up 3, I end up at 4. Well, wouldn't that be 7? If I start at 7 and back up 3, I end up at 4. So there are the coordinates of point D. Okay, number 13. We got a couple of people, they have a puppy, they're both pulling on the puppy and he's pulling back. And we're hoping that the dog is at a standstill. Those forces are balancing each other out. So let's find the magnitude, or we're going to find the magnitude, but let's find the resultant force. So let's look at the little girl first. Her vector is magnitude 23 at an angle of 18 degrees. And that angle is in standard position, so I'm going to go ahead and use that angle when I write the coordinates of my vector. So x for the girl, x will equal magnitude times cosine 18, and y will equal magnitude times sine 18. So those are the components of the girl's vector. Now what about the boy? Well, his angle is 15, but notice standard position, and his magnitude is 27. So his coordinates are 27 cosine -15 and 27 sine -15. Okay? Now, we're going to add those together. So we are going to find the resultant, the sum of those two vectors. We want to find out how hard are they pulling together. And then the dog is pulling back that much. So here we go. Add these together. I need my calculator. So 23 cosine 18 plus 27 cosine -15. Remember, we are adding the x's and adding the y's. So my resultant vector, the x is 47.95, and the y, 23 sine 18 plus 27 sine -15 is 0.12. Now, what is the magnitude of that force? That's what I want to know is, what is the magnitude? So, the magnitude of that force, I square the first one, I square the second one and take the square root. So the magnitude of the force actually is about 47.95. This number is really, really tiny. So when I squared it and added it, it didn't make much impact. But there it is. So it's 47.95 pounds. The magnitude of the resultant. This vector is the resultant. I added my x's, added my y's. This is the magnitude of the resultant, which is what the question wants to know. How hard is he pulling? Not what direction is he pulling or anything like that. How hard is he pulling? What is the number? Like she is 23, he is 27. That dog is pulling back 47.95 pounds. Okay, perfect. We are done with 6-1. That homework date has been published, so I can't remember what it is right off the top of my head with all our virtualness and all that stuff going on. I don't even know, but it's in there. Check School of GNC. Now we're doing 6.2. We're going to find what we call the dot product. Now let's get a couple things under our belts here. When we multiply vectors, there are actually two operations, two completely different operations. In regular arithmetic, if I say 2 times 3 or 2 times 3, it doesn't matter. The dot and the X symbol, they mean the same thing. It means multiply. Not in vector land. In vector land, if you use this symbol, it means one thing. And if you use this symbol, it means an entirely different thing. This is called the dot product, and this is called the cross product. And the biggest difference I can tell you right off the bat is the dot product is a scalar. So in other words, when I calculate a dot product, I'm going to get a number like 12. When I do a cross product, I get another vector. Okay, they are completely different. So because of that, we never say V times U. That doesn't that doesn't make any sense. We always say either V dot U or V cross U. Now today's lesson is all about the dot product. Today we're going to be dotting. So V dot U is the dot product, and our answer is going to be a single number. It is so easy, you're going to be amazed. So we are going to find the dot product of the vector whose coordinates are 1, 2, and the vector whose coordinates are 6, 3. To find the dot product, we simply multiply our x components. So we're going to do 1 times 6. And then we multiply our y components, 2 times 3. And we add those together. Remember, I told you it would be a number. And it is, it's a number. 1 times 6 plus 2 times 3. So the dot product is indeed 12. Just 12. B. We're finding the dot product of 3, negative 4, and 8, 6. All right, so we take x times x, so 3 times 8, and negative 4 times 6. And so what do we get? Oh, looks like we get 0. Did you get 0? Oh, that's kind of special. 0 is a special number. Let's take a closer look at these two vectors before we move on. Look at the vector 3, negative 4. The vector 3, negative 4 goes over 3, right? 3, and down 4. So if you were going to draw a picture of it, a position vector, that's how you draw it. Over 3, down 4. Now, we talked a little bit about this in the last video, but when we look at the coordinates of a vector, it tells us how it's moving. And in 2 dimensions, how it's moving is like slope. Isn't slope how a line moves? Well, the coordinates, the directed distance, this right here, the vector components, that's basically slope. It tells me I'm going right 3 and down 4. So the slope of that vector is -4/3, y over x. -4/3. Now what about the slope of this one? Well, the slope of this one's going right 8 and up 6. So the slope is 6/8, which reduces to 3/4. So wait a minute. The slope of this vector is -4/3. The slope of this vector is 3/4. What's the relationship between those 2 slopes? They are opposite reciprocals, which means the lines are perpendicular. When the dot product is 0, it means your vectors are perpendicular. Now, we throw a new word at you. It's actually over underneath 2, problem 2. The word is orthogonal. Okay, I think you're starting to get the idea that Vectorland has its own vocabulary. We don't talk about length, we talk about magnitude. We don't talk about sum, we talk about resultant. We don't talk about perpendicular, we talk about orthogonal. Orthogonal is the vector word for perpendicular. So make a little note that if v dot u is 0, then the vectors are orthogonal. Now, you're thinking to yourself, okay, that's interesting, Mrs. Ford, I'm so glad you told me that, but how is that at all useful? Well, I want to remind you of something. Here, absolutely, we could tell these 2 things were orthogonal because we could find the slope of this one and the slope of this one. We knew they were opposite reciprocals all as well. The problem is, slope is a 2-dimensional thing. I mean, think about it, it's y over x, 2-dimensional. As soon as we move to 3 dimensions, then there isn't any more slope. So in 3 dimensions, we need, when we have x's, y's, and z's, which is what space is, we need a way of telling relationships between vectors. Are they parallel, are they perpendicular, whatever, and we can't use the concept of slope. So for orthogonal, the way you're going to tell, always and forever, if vectors are orthogonal, you're going to dot them. You're going to find their dot product, and if their dot product is 0, then the vectors are orthogonal. Okay, well, enough of that. Okay, let's look at problem C. Now, problem C is set up a little bit differently. Problem C is set up as a couple of different vectors that are forming an angle. And the length of this vector, notice the notation with the absolute value, the length of this vector is 10, the length of this vector is 11, and the angle they're forming is 72 degrees. Now, your job is to find the dot product of these 2 vectors. Okay, we're going to find the dot product. In order to do that, we have a couple of options. We could find the components of these vectors, but that would be a little complicated and a bunch of work. What I mean is we could find the x and y that go with those vectors. That would take, I don't want to do that. Luckily, there is another way to calculate the dot product. And the way you use will be determined by how your vectors are given. If your vectors are given in component form, then you're going to do x times x, y times y, and add them up. But if your vectors are given more in terms of like a physical problem, where you've got vectors out there doing things, then we can find the dot product by taking the magnitude of the first one times the magnitude of the second one times the cosine of the angle between the vectors. So this is another definition of the dot product. Magnitude times cosine. Well, we have exactly what we need. So it's going to be 10 times 11 times cosine 72. So again, that's just going to be a number. 33.99. Now that's a really handy thing to know. Because look at the next question. We've got these random vectors, and I could draw them, but I'll draw them this time, but I won't be drawing them usually. Just extra work I don't need to do. This is 1, -4, and this is -3, 2. And I want to find the angle between them. I want to find the angle between them. Now, I want you to think about what we just talked about. The angle between them, between two vectors, is part of the dot product definition. But in this problem, I know my coordinates. So I can actually find the dot product. 1 times -3 plus -4 times 2, -11. The dot product is -11. But I also know that the dot product, the same dot product, is the magnitude of the first vector. Okay, what's the magnitude of that vector? We talked about this yesterday. The magnitude of the vector is the square root of 1 squared plus 4 squared, so that's going to be root 17. If you're confused by that, use your picture, set up the Pythagorean, or set up a right triangle and do the Pythagorean theorem. And this magnitude is the square root of 9 plus 4, 13. So I don't know what the angle between these vectors is. I have no idea what that angle is. But I know that the dot product is the magnitude of the first one times the magnitude of the second one times the cosine of that angle. That's a definition of the dot product. There are 2 definitions of the dot product, 2 ways to calculate the dot product. I can do it coordinate-wise, which gave me -11, but I can also do it using the angle, magnitude times cosine. Well, since both of these are dot products, I can set them equal to each other. So -11 equals root 7, let's see, what's 17 times 13? 221 times cosine theta. So -11 and this are equal. Now I can multiply a square root times a square root and I just get a bigger square root. So the cosine of theta is -11 over root 221. So now we'll second cosine, -11 divided by square root 221. I get 137.73 degrees. So the angle between those 2 vectors is 137.73. Given any 2 vectors, you can find the angle between them by doing this, using both definitions of your dot product, setting them equal, and solving. Okay, let's look at the next one. Now our vectors, we're gonna do exactly the same thing, but our vectors are negative 6, 4, and negative 8, negative 12. All right, my job is to find the angle between them. So what do? Well, first I find the dot product. So the dot product is going to be, wait. Is that 0? Whoa, that's important. I just erased it. Let's see what happens. Let's just keep going. We know what the answer is already, but let's just keep going and see if it all works out. So one definition of the dot product is x times x, y times y, add them up. Did it? Okay. The other definition of the dot product is the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle I'm looking for. In this problem, we are looking for the angle between the vectors. Okay? Now, what's the magnitude of the first vector? Well, remember, to find magnitude, you simply square, add them up, and take the square root. It's the Pythagorean theorem. I'm not going to do this again. This is one more time for those of you that don't see what's happening. We're going left 6 and up 4. So to find the magnitude, we're going to square that, add them up, and take the square root. Okay? So 36 plus 16, 52. Okay? And then here, 64 plus 144, 208. I'm not worried about simplifying those. I'm not worried a bit. For my own sake, I do like to multiply those together, so I only have one radical. Makes it easier for me to type in 10816. So my dot product is this, and my dot product is this. So I'm going to set those equal to each other. So 0 equals the square root of 10816 cosine theta. So cosine theta equals 0. Well, what angle has a cosine of 0? You should know that. But if you don't, second cosine 0 on your calculator, and what happens? The angle between these two vectors is 90 degrees, which means they are orthogonal. The vectors are orthogonal, which I knew right here, because I had it written up here, something for you to know, that if v dot u is 0, if the dot product is 0, then the vectors are orthogonal. So what is the angle between these two vectors? 90 degrees. They are orthogonal. Somebody else might say, Ms. Ford, what about 270? Well, I want to remind you that if I've got two vectors, I'll draw them like this, and that's 90 degrees, then the other angle between them would be 270. We always go with the smallest one, okay? So there's always going to be two angles. There's always going to be the little one and the big one. Always go with the little one. So these guys are 90 degrees apart. All right, so number 3 says, determine whether the following are parallel, orthogonal, or neither. Okay. All right, so what do we got? We've got negative 1, 3, and 6, 2. All right, so let's do our dot product first. So our dot product is negative 6 plus 6, 0. Tell me about the pair of vectors in problem A. The pair of vectors in problem A are orthogonal because their dot product came out to be 0. All right, let's look at the next two. All right, let's do their dot product. Negative 2, oh boy, okay. I don't know what they are, but I know for sure they are not perpendicular. They're not orthogonal because their dot product did not come out to be 0. So now I have to stop and think, are they parallel? Now, In 2 dimensions, you can always, always, always fall back on slope. Always, kids, for everything. In 2 dimensions, you can always go back to slope. So if we do that, what is the slope of this vector? Well, the change in y is 3, the change in x is -1, so the slope of this vector is 3 over -1. Now what about this vector? Well, the change in y is -6 and the change in x is 2, so the slope of that vector is also 3 -1, or -3. These guys are parallel. Now, what if I can't use slope? Let's just expand this a minute and pretend that I'm in 3 dimensions and I'm comparing 2 vectors. I can't use slope. So how do I know things are parallel? Well, if vectors are parallel, then they are scalar multiples of each other. So in other words, if I had the vector 1, 3, then 2, 6 is called a scalar multiple. I just take 2, whatever scalar I want, in this case 2. 2 times those gives me this. So any scalar multiple, so if I multiplied by -4, it would be -4, -12. Any scalar multiple, multiply by a number, any scalar multiple is parallel. So if I look at these 2 vectors, it looks to me like if I take this one and times it by -2, I would get this one. In other words, it looks like U is -2 times V. Double check that. -2, -2, wouldn't that give me U? And if you can have this relationship, if you can write one vector as a multiple of the other, then they will be parallel. Always parallel. So those 2 are parallel. All right, what about V? Or C, moving around here. C. My vectors are 1, 0 and 0, 3. Let's do the dot product first. So it's going to be 0. Okay, what's our relationship? Those 2 vectors are orthogonal. You, if you're not asleep by now, you know that that vector starts at the origin position vector and takes 1 step to the right. This one takes 3 steps up. Doesn't it make sense that if this one is horizontal and that one is vertical, that they would be perpendicular to each other? Absolutely. Dot product 0, these guys are orthogonal. And finally, all right, so we're going to do our dot product. We get, nope. So they're not perpendicular, not orthogonal, okay? Are they multiples of each other? Well, the answer is no. No, because I could multiply by -2 and get 6, but if I times this by -2, I don't get 2. These are not multiples of each other. -2 times -3 would give me 6, but -2 times 1 does not give me 2. The slope of this one is 1 over -3, and the slope of this one is 2 over 6. They don't match. So they're not perpendicular, they're not multiples of each other, so they're not parallel. That means they are neither. All right. All right, this next one, I should have, I copied this out of your textbook, obviously, and I should have included the picture because it's a little bit hard to understand what's going on. But here's the situation. Here's Juan, here's the hill, 45 degrees, and Juan is sitting on a sled up here, okay? And Rafaela is holding on to him. So he's on the sled, he's gonna go down the hill. She's got like a rope around him or something, and she's holding him. So she's holding him, and he's not moving. So the question is, what's the force required to keep him from sliding down the hill? Okay, now what do we know? We know that the sled and Juan are 140 pounds. Okay, so Juan, 140 pounds of force. That's what that vector is, 140 pounds. She is holding him and keeping him from sliding down. So we need to know what her force is to stop him from sliding down. So I'm going to make another little right triangle here. And I'm going to figure out what this force has to be to keep him from heading down the hill. So this force of 140 pounds is pulling down. We need to stop that. How big does that have to be to stop him from scooting down the hill? Well, tell me what I know about anything here. Let me back up for a second. Let me take this out for a minute. Would you agree that this angle right here is 45? So let me put this back in, this perpendicular back in, perpendicular force. Look at this little triangle here now. If that's 45, then this would be 45. I know the vertical pull of the sled and the kid is 140. I need to find that number right there. Well, simple right triangle trigonometry, right? I mean, yeah, we can do that. If I use this angle right here, I can say the cosine of 45 has to equal adjacent over hypotenuse. Keep in mind I'm looking at this, the little right triangle, so 140 is the hypotenuse of that triangle. And so x is 140 cosine 45. So 140 cosine 45, 98.99 pounds. So she has to pull with a force of about 99 pounds to keep him from sliding down. Now, you might be thinking, well gosh, if he's 144, doesn't she have to pull with 144? Or 140, I mean. If he's 140, doesn't she have to pull with a force of 140? Only if they're pulling in the same direction. So, for example, if we had him suspended on a, like I'm holding him, and he's 144 pounds straight down, 140 pounds straight down, then I'm going to have to pull with a force of 140 straight up, because I have to counterbalance that entire force. But for her, the hill is actually absorbing some of the force. His pull is vertical, but he's not falling vertically. He's falling at an angle. So that takes care of a little bit of the force, and she only has to pull back with what's left. And what's left is that much. All right, good deal. What's next? Oh, we got the same kind of problem. Good. Now this time though, we got a car on a street. So it's exactly the same kind of situation. So let's see if we can make this one make good sense to you. All right, so here's the street, and the angle of the street is 12 degrees, which is a pretty steep street, you guys. I mean, I know you're thinking a 12-degree angle, that's not much. That's actually pretty steep. And we have a 200-pound force. So that's the weight, that's vertical. That is the vertical weight of this car. We want to find the magnitude and force required to keep the car from rolling down the hill. So that's exactly what we're finding over here. What is that force that we have to apply to balance out that part of the pull of the car going down the hill? So I'm going to go ahead and make my perpendicular. Oh, I did the same thing. Remember, if you look at the big right triangle, if that's 12, then this guy right here would be 78. Would you agree with that? And I want to find this. So this is question A. So for question A, we're going to look at this little right triangle right here. We're going to figure out what that force is. So cosine 78 equals x over 2,000. For 15.82 pounds. So to keep this car from rolling down the hill, if it were up to you, if you were the person responsible for keeping this car from rolling down the hill, that is how much force you would have to exert in order to stop that. Now, find the force perpendicular to the street. That's this, I'll call it Y. Here's the street. This is the force perpendicular to the street. You found the force parallel with the street, because that's how you're pulling it. Now we're going to do perpendicular to the street. So we can do sine. So sine 78 equals a Y over 2,000. So 2,000 sine 78 1956.30 pounds. That's the force perpendicular to the street. All right, we're going to do these last three problems and then I'll just shut up. How about that? So the last three problems, if you read through them, they all involve the physical concept of work. In physics, work is defined simply, it can be more complicated, but simply, work is defined as force times distance times cosine of angle between. Whoa, 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 stop right there. Force times distance times cosine of angle between. What does that sound like? I know the words are a little different, but force is a number, a scalar. Distance is a number, a scalar. So I've got a number times a cosine of an angle between those two quantities. What is that? That's the vector dot product. So work is an application of the dot product. Hence, it's in this section. It's an application, an actual, useful, practical, real-life application of the vector dot product. So here we go. Find the work done lifting a 2,600 pound car. So the force is 2,600. The distance is 5.5 feet. And now I need the angle between them. Now this one isn't complicated. Pretend I'm like some super strong person. And I am, here's my car, down here on the ground is my car. And I'm gonna lift that car straight up. My force is vertical. The car is moving vertical. It's not on a hill. It's not like the problems I just erased. It's not on a hill. I am lifting this car straight up. So the angle between is 0. They are in the same direction. When your force and your distance are in the same direction, then there's no angle between them. The angle between them is 0. When I was holding the sled from going down the hill, then my force and my distance were in different directions. But now, they're the same. So what's 2,600 times 5.5? 14,300. And the unit we use, when the force is in pounds and the distance is in feet, we use a unit called foot-pounds. A new unit of work is foot-pounds. You are moving something that weighs pounds, a distance in feet. So the work that you exert, in this case, is 14,300 foot-pounds. By the way, the cosine of 0 is 1, right? The cosine of 0 is 1. So if they are acting in the same direction, the force and the distance, then it's just force times distance. Now, problem 7 is a little different, because problem 7 says, I have a force of 12 pounds acting in the direction of 1, 2. So my force, I'm going to just put 1, 2 here, and I'm going to move it 4 feet horizontally. So the thing is moving horizontally from 0, 0 to 4, 0. So it's moving a distance of 4 feet. But I'm not pulling it horizontally. It's like I'm pulling a wagon, all right? Here's my handle of my wagon. And the wagon is rolling horizontally, but I'm pulling it this way. So my work is going to be 12 times 4 times the cosine of whatever angle that is. Now, kids can't just drop a perpendicular. That isn't how this works. You've got to understand that this force is acting in the direction 1, 2. So if I came over here to the side and I drew that force, just the force that's moving over 1, up 2. How big's that angle? What can you tell me about that angle? Can't you tell me that whatever that angle is, its tangent is 2 over 1? Right? Now, I'm not talking about any distances, any forces. I'm just saying I got a vector that moves over 1, up 2. I need to know that angle. And it doesn't matter how long I make it, that angle isn't changing. That is the angle for this vector. I really don't care about the tangent though. I'd really rather have the cosine. That's what my formula requires. So what if I do my Pythagorean theorem here and get root 5? So for this angle, theta, the cosine of that angle is 1 over root 5. So when my formula says force times distance times cosine of angle between, that's 1 over root 5. And that will be the answer to my question. Please don't say cosine that. That is the cosine. The cosine of the angle is 1 over root 5. So I got 21.47. And again, that would be foot-pounds. Okay. All right. One more. And then you can turn me off. Okay, one more. Here we go. What's going on this time? I got a force of 50 pounds acting in the direction 2, 3, moving an object 5 feet from 0, 0 to a point in the first quadrant along the line y equals x. So here's the line y equals x. This is my object moving. My object is moving along that line, and the distance it is moving is 5 feet. Remember, work is force times distance times cosine of angle between. That's the angle between. So I know my distance is 5. I also know my force has a magnitude of 50. And the force is acting in the direction 2, 3. All right, now you're going to have to use some logic here. I'm going to try to draw a picture of this. This guy is moving along the line y equals x, which means over 1, up 1, over 2, up 2, over 3, up 3, and so on. The force is acting in the direction over 2, up 3. So isn't the force up here somewhere acting in the direction over 2, up 3? Another way to think about that is the slope of this line is 1, y equals x. The slope of this line is 1.5, so it's steeper. Here is the angle between them. I'm going to get rid of that. There is the angle between them. Your job is to find the cosine of that angle. That's what's going to go right here. The cosine of that angle. Now, the angle has nothing to do with the length of these two lines. Here's what I mean. There's theta. Has theta changed? Has theta changed? Has theta changed? No. So the length of those two vectors has nothing to do with theta. So what I'm going to do is I'm going to assign my black and my red vectors coordinates. So I already know this one, the black one, is the line y equals x, which means over 1, up 1. So I'm just going to use over 1, up 1. Now, if you did over 2, up 2, over 3, up 3, I don't care. It doesn't make any difference. As long as they're in the ratio 1, 1. That's it. Those are the coordinates. That's the direction of this. Now, what about the red one? Well, they told us that one was in the direction 2, 3. So I'm just going to use 2, 3. If you want to use 4, 6, or if you want to use, I don't know, 2 root 5, 3 root 5, I don't care. It doesn't make any difference as long as they are in the ratio 2 to 3. So I have a vector whose coordinates are 1, 1, or whatever you've given it, and 2, 3, and I want to know the angle between them. Wait a second, didn't we do that earlier? The dot product of these two vectors is 2 plus 3, which is 5. And doesn't the dot product have to equal the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between? Isn't that what I need right here? So what is the cosine of the angle between? 5 divided by root 26? Now you could find that angle, you don't need it. All you need is its cosine, and you know its cosine is 5 over root 26. So the answer to the problem is 50 times 5 times 5 divided by the square root of 26. So 245.15 foot-pounds is the answer to the question. All right, hope you're having a great day. Oh, by the way, 6.2, that homework will also be posted. We just finished that, so that'll also be due.